Welcome back, everyone, and today is going to be a special day. Today is whiteboard day. We're going to spend a lot of time kind of just going through some theories and ideas because today we're going to build a particle system. A viewer asked about me creating an effect, and in previous videos we've created effects before, but we had to code everything. Had to code the shaders, all the buffers, and everything else, especially when it comes to particle effects. So I was thinking, you know what, since effects is like a big deal, and I really do want to do more of them. It's about time we created a particle system. It's kind of like how Unity makes making particle effects so easy. You just apply a bunch of features. You put a couple of settings in. You put in a couple of images, and in the end, maybe a mesh or two. Overall, they make particle effects very easily as long as you know what you're doing. So what we're gonna do is build a particle system. So something that we can kind of just add in options and put in some bits of information, and everything gets handled for us. So we've done particle effects before. Like I said, we had to do everything manually. Today we're going to try to build it in a modular way, so this way it's more dynamic. And we're going to also strive for efficiency. So one of the big changes we're going to do, we're going to go to more advanced data management, is interleaved data. Previously, when we were doing particle effects, we did transform feedback. And transfer feedbacks allows us to push all the data to the GPU and then have a shader program actually do all the mathematics and updating a separate buffer. And then we use the two buffers that alternate back and forth to actually as a drawing buffer. So we're gonna go through that all again today, but more a higher level. Like if you're really interested in transfer feedback, go look at my previous videos about particle effects, and I go into more detail about that. Today we're going to deal with interleaved data, how that's a little bit different, and that's how more efficient. So interleaved, up until this point, we've had to deal with we dealt with data in a silo kind of effect, in a way, a silo way. Each buffer was one array. And typically, when we need to create vertices, we need different types of data. Some of the main data that we need is vertices, UV, and normals. So you can see there's three parts, which is X, Y, Z. This is ST, could also be XY, and this is also XYZ. So that's a vec3, a vec2, and another vec3. So that determines all the data normally for our mesh. Okay, so when we deal with buffers, this is like one array, that's another array, and that's another array, and we create an array or a buffer for each array, and we store that information into to the GPU. Now this is considered just separate data. Now if you want to interleave the data, we've done it once or twice in the past, but we haven't dealt with it because it's kind of complicated when you're dealing with it in the manual sense. But in this lesson, we're going to have it done programmatically for us, dynamically. So we just push in, we're going to be able to push in arrays of data, and then what comes out is one big interleaved data array. So what does interleave mean? Interleave means we're going to have all our arrays combined into one massive array, and everything's going to be organized one chunk at a time. So I have this kind of highlighted. This part right here is considered one vertex. Remember, we're going to have our position, and then we need to, it's attribute what UV data is applied to that vertex, and what normal data is applied to that vertex. So that whole row, and then we kind of have like a fourth one, which is like an index that we use to kind of tie everything together. But like I said, this is these are three arrays essentially, and three buffers that we have to create on the GPU. What we can do is interleave the data, so we can have this whole chunk. Sorry for the bad drawing. That whole section that first, like let's say index 0, 1, 0, 1, 2, and this one will be 0, 1, 0, 1, 2. All of that will be compiled into one piece of the... Wow, I draw horribly. So how much is that? That's 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so all that gets compiled into an array. All right, so we have our V, V, V. Then we have our UV, and then we have our normal. So all that gets copied over, and then we kind of loop through the array again and repeat the process. So it will be VV, UU, and then for the next set. So like I said, that's what interleaving arrays are. It's just we're compiling all the data into one array, and we're alternating back and forth. Now, what this creates in code that we use is called the stride. Now, the stride value when we assign buffer information is how long that piece of data is inside our interleaved data. So stride is used for interleaved data. We usually set it to 0 because we have all our data separated into separate buffers. Since we're not, we have to now define how big is each element. That's usually what's called an element of data, because each element can have different types of chunks or different types of attributes. So each element has several attributes. Like this one element has 3 attributes. It has a vertex, UV, and normal. So 3 attributes for this one element. So the stride is size in bytes. That's what stride equals to. So we have 8 floats, right? So that's 8 floats times a float is worth 4 points, 4 bytes. So it's 8 times 4. And essentially that should be it, right? 1632. So it's 32 bytes long. And that's it. And that's the side of our stride. And then we have to deal with an offset. So when we assign, the buffers, this one buffer to an element, we bind this one buffer, we tell it the size in stride, in bytes. Then we also then have to define each attribute, and each attribute has to be defined by an offset. So the offset for the first attribute is 0, because it starts at 0 bytes. The next one starts 3 times 4, which is 12. Then the next one where n starts, it's, let's see, 1, 2, 3, 4, 5. 5, what's 5 times 4 is 20. 20. So that ends up being the offset. So the stride is always going to be 32. And then for V, the offset's going to be 0. For UV, the offset's going to be 12. And for normals, the offset is going to be 20. And when we assign that bit of data, when we create our buffers, that will then allow us to use the interleaved data as attributes in our shader. Now, why am I going to go through all this hassle of interleaving data together, which in the past it's been pretty easy to just keep everything in separate silos, right? Why go through all this mess, right? The problem is it's kind of hard to explain to a JavaScript developer how important doing it, how efficiently it is to interleave the data and then have everything set up with like these kind of offsets. This is because, don't forget, all this stuff is written in C and C++. And when you're dealing with the memory directly, you have something called pointers. And pointers are like these memory addresses to information in RAM. So the easiest and quickest thing to do is keep everything in arrays, and then use the memory addresses, because then all the memory addresses are incremental to each other. With all this information that we have, we can then very easily just say, here's the memory address that starts the array, and just add 32 to it. That means that's the whole chunk. And if anything, all you have to do is just say, I want to add 0. So I know from 0 to here I have this information. and then the pointer is now at this point. Then you add another 12, and you get that. And then you add another let's see, 3 times 4 is another 12. Well, this is 8. No, 8, 4. It's 2 times 4 is 8. Yeah, and this is another 12 over here. So this information helps it to kind of just take in a memory address and add to the memory address, and easily traverse an array of information, as opposed to having everything in separate buffers where you kind of have to go, all right, I have to keep track of where I'm at in this array, I have to keep track of where I'm in this array, and I have to keep track of this array. And then I have to go to RAM over here to get the information, then I have to go to RAM over here to get this one, and so forth and so forth. And the more data you have, the overall in microseconds, the slower it is. And you have to think about it, we're dealing with tons of vertices sometimes. So any way you can shave off milliseconds adds up to quite a lot when you're dealing with hundreds and thousands of bits of information. So if we get rid of all these buffers, that means we have to do less memory lookups, and we have to track less memory in all. And then we could just, so we have one bit of information, and since we know how to kind of traverse it, we can traverse it very quickly because we know how to move through it. It's kind of like knowing the path, and you only have a single path, and you know the right steps to take. It makes everything so much easier. So that's the reason why we're going to do this, because in terms of memory management and efficiency of traversing memory, doing it this way increases your speed. And like I said, you're dealing with less memory. And on top of that, you're only doing one GPU call. Instead of me uploading 3 bits of information or 3 arrays of information, I only upload 1 array of information. So this time I'm doing only 1 GPU call as opposed to 3 GPU calls. So you're increasing the efficiency of GPU calls in general. So this big, huge tirade of how to do interweave, that's going to be really the crux of what we're doing. So that's going to be like step 1. We need to be able to take all our information, interleave it, and get it and create all the information that we need to tell the OpenGL or WebGL how to traverse that bit of information. So we need to figure out its stride, which is just the size in bytes, and then the offset is also where it starts in bytes inside that stride. All right, so that's really, because like I said, we haven't really talked about interleaved data, and now we're going to do it. And now we have to do is a transform feedback, right? So the next thing, I'm not going to deal with it too much. I have notes too, so I'm more organized for this video because it's more complicated. So when I was trying to create this particle system, I wanted to kind of create one big buffer for our free transform feedback, and apparently you can't do that. Because if you're going to read and write, you can't really read and write to the same buffer as a piecemeal. When we create interleaved data, we read it in chunks of stride. So elements are broken out by stride. And when we write to a buffer, like through transfer feedback, there's no stride. So if I have like some information. So I have, let's say, 1, 2, 3, 1, 2, 1, 2. All right. So let's say this is stuff I want to be able to write. This is stuff I want to be read-only, and this is stuff I want to write. So like this is binary. This is that's one attribute. R is another attribute. W is another attribute. So I read all this into my transform feedback, but I only want to update this and this. But this whole thing is one element or one stride of information that we're currently processing or we're dealing with. Now, we can read in all this information. Like this is RW, really, each one. These are just reads because I don't want to update them, because some information we don't need to update. So we got 3 read writes, 2 reads, and 3 other read writes. Now, if I want to, I read all the information, then I want to go write. It's going to write. Let's say I want to write this. Let's say this is 1, 1, 1. This is B, B, and this is 2, 2, 2. When I go to write, it's going to write 1, 2, 3, 4, 5, 6, 7. It's going to do 1, 1, 1. That's great. 2, 2, 2. And it's not going to do anything else to the rest of the data. Now, here's the problem. You're already seeing that the certain data got overwritten. My 2 reads got overwritten because when you rewrite for transfer feedback, it completely ignores the stride. It just writes it in order. So that became a big problem. That actually wasted a Saturday. If you're following me on Twitter, I ended up writing a comment about it and then quickly explaining why, if you're dealing with transfer feedback, you can't combine read and write data, or read-only data and write data in the same buffer, because the writing does not take stride into account, and it automatically overrides data. So my B data has been completely wiped out. That's just how it is when you're dealing in C++. You have to know how to handle your memory correctly, else you're screwed. So even though we're doing WebGL and we're doing in JavaScript, we still have to remember that when we're dealing with the GPU, you have to deal with it as a C++ programmer. You are actually modifying memory and arrays and things like that. Excuse me, turn this off. Okay. So since I discovered you can't read and write in one big buffer, plan B was, and which worked out really well, is that I need to create 2 buffers. You gotta create 2 separate buffers for transform and feedback. I can't create 1, I have to create 2. One is for only read, and the other one is for read and write. And I know I did a bad W, but that's like a cursive W, right? So in our read buffer, we can have all the static information we want. And in our read and write, we put everything in the order that we need to write it to. So this way, we never end up overwriting our read stuff. And this is actually more efficient because of how we have to set everything up. But we also need one more buffer that we need to set up. And this one is going to be just like read, but this is going to be for our drawing or for our rendering. So to do our transform feedback with a particle system, we need 3 buffers, right? All 3 buffers will have interleaved data, and 2 of these are read-only. That's read-only, and draw is also a read-only. They're both read-onlys. Now, the only difference between this one and this one is that the draw buffer will have our vertex, our UV, our normals, maybe our index. Well, index can't be interleaved because that's integer data. We can only interleave. I think we can, but I don't want to deal with it. But that makes sense. I think complicates things a little bit. But we're just going to interleave float information only. So an index has to be its own buffer anyway. So can I undo that? There we go. So vertex, UV, and normals. So it's going to have that chunk of information, all interleaved, V, U, N. Our write data is going to have whatever we need to write. Sometimes like we need position. Could be velocity. Position. Velocity can sometimes be read-only if I don't want the velocity to change. So, velocity. Time could be static. It really depends. We have to, depending on the settings we want, things we're going to be moving back and forth. And so, overall, that's okay. So, who cares what data? We just need data. Okay, so we need data for reading and data for writing, and these 2 are going to be used in our transform feedback. That stuff is what's going to be looped, and this bit of information is also what we're going to use to instance that data. So this draw buffer is going to have, let's say, our quad. So it's going to have all the vertices we need for that quad. And this one is going to have vertex information for instancing. So this way, if we have, let's say, 4 elements of information, each one has its own sets of attributes. That means we want to draw the quad 4 times. So this information is how many times we want to draw our draw information, but with additional attributes that that defines each instance of that quad. So that's where that's how we do transfer feedback. This defines our instance data. This defines what we're going to instance, what we're going to duplicate. How many copies of this are we going to do, and what changes need to be done? Like position might change. That's something that's going to change a lot, because we're going to move this quad around, and this transfer feedback ends up calculating the movement. And the last thing we need to do in transfer feedback is that we need to set up 4 VAOs. We don't need to, but it makes it so much easier. And 2 transform feedback. So we need 2 VAOs for TF. That's VAO A, VAO B. This is going to have a shared copy of our read buffer, but it's going to have an individual copy of our read-write buffer. So our read-write buffer is going to be duplicated twice. We have to duplicate it twice. Now, why do we have to duplicate it twice? Now, if you never did transform feedback from the previous videos, you're new to this. The reason why was, I did this wrong, B, because I wanted to note that this is different. The way transfer feedback does it is that we're going to read from A, right? We're going to read from here. We're going to read all this information, but we're going to write to B. In the next loop, we're going to read from B, and we're going to write to A. So we're going to alternate back and forth for every loop. And let's say loop 0, the starting loop, we're going to read from A, we're going to write to B. The next loop, we're going to read from B and write to A. And that's what transfer feedback is all about. That's why it's called a feedback. A feedback loop is something that kind of just starts and ends back and forth. It repeats over and over again. So we're just going to feedback back and forth. We're just going to just keep going back and forth. Our read data is static, so that's why we have a shared copy of it. And this, our read-write data, is duplicates, because we need to change it. For every loop, so let's say our read-write data is position. So let's say position A equals 1. And we're going to update it and say we're going to save it to position, my God, I'm horrible at typing. Position B now equals 2. We copied it. In the next loop, we're going to read from position B. I don't know why I want to keep on saying B. Position B, which equals 2, and we're going to update it. And we're going to save it to position A. Now it equals 3. So we just keep incrementing. See, that's kind of like the flow. That's the feedback loop that we're creating. A equals 1. We add 1 to it. That's what our shader is going to do. Now it's 2. So now in the next loop, we're reading from B. It's 2. We're gonna now the shader code says just to increment, so that we save it to A, and then back and forth, back and forth, back and forth, back and forth. Eventually, position is going to be moved. And the final step is that the final VAO, the last 2 other VAOs, is for drawing. AO, B. And this is for drawing. And let me get rid of some of this crap. Oh, I said that C word. I might get flagged again. I get flagged for all my videos now because I say like crap and other words. So we got 2 VAOs. So we're gonna have like 2 other VAOs for our drawing. This will have our draw buffer. It can also have our read buffer if we want to, if we need to. And it will have our write A, write B. So when we write to B, we're going to draw from B. when we write to A, we're going to draw from A. So we alternate back and forth with our transform feedback to read to write the data, to read and write the data, and then we go to drawing. We end up just drawing the VAO that has the data that was updated. So if we updated B, we used the VAO B for drawing because that has the updated information. And then in the next frame, we're going to update A, so we're going to draw from A. So we're going to load that VAO. And why I say 2 transfer feedbacks is we just have to set up 2 transfer feedbacks, and all this thing does is defines WA and defines WB. That's all this is. It just defines a read-write access to this buffer. Because this buffer is read-only until you define it as a transfer feedback buffer. That's it. You just assign it, say, hey, this thing is read, and then you can use it as a read. And then we have to load, so when we do this, we have to load up VAO A, but then we have to do transform feedback B. That's how we read from A, write to B, and then vice versa. VAO, I'm getting close to my little marker here. VAO, transform feedback A. So we just alternate back and forth. So, like I said, if you've done transfer feedback with me with our previous particle effects, it's the same idea. It's this, this is for new people who see this video, or maybe I went in more depth than I probably should have. I don't know, but this is the idea of our particle system. So now we know how we're going to process information. We know how we're going to store the information, right? Now it's down to the last bit of things we need to do to create a particle system. How are we going to organize information? Or what is the code going to be like? So the first thing I'm going to do is create transform. We're going to create a class that handles just the transform feedback. We're just going to, I want to be able to just pass, I'm sorry for my horrible writing, pass data, whatever. I'm going to pass data to it, and it's going to turn the data into interleaved data, and it's going to pass it to the GPU. It's also going to create all our VAOs and transform feedback stuff on the GPU. It's also going to calculate all the strides and all the offsets as it's building the interleaved data. And it's going to handle the draw, which then handles swapping between the different between A and B. So every time we tell it to draw, it's gonna do A and B, or it's gonna do B and A, either or. It's gonna do the transfer B feedback, then it's going to do the drawing, swap, then draw, swap, write, I guess, whatever. So we're going to have one class called that does that. And the other class we're going to have is a parent class. The parent class is going to be our particle system. Now, our particle system class is going to generate the data based on settings. So this thing generates the data and then passes it to transform feedback, and then it creates this entire process with the data. So that's how I built it, because I wanted the pieces to be separate, because then I can reuse transfer feedback in anything I want, or it could be as a good sample for anyone like you guys who maybe you're doing in C++ or in another languages in Java. This object that just handles transfer and feedback. It doesn't deal with data at all. You have to give it the data, but then it breaks everything out into its own silos based on certain settings. So this way you can then use it. And in the particle system, like I said, I just want it to be this actual system that I tell it, okay, I want to set positions in a circular way. I want some colors to alternate, whatever settings. Handles modules. And I don't know what to call it. I don't know if I should call them. Right now I call it modules, but maybe call it modifiers. Maybe call it modifiers. And these are just little chunks of code that we can apply to. So it's dynamic. So like the whole thing is like the particle system itself doesn't know what to do other than it has a stack of modules ready, or has a stack ready to apply modules. And each module is basically a setting. Like how many particles do we need? What colors are they? How fast should they be going? So each one of those questions is a module or is a modifier. I probably really should call them modifiers. But like I say, in the code right now, I'll call it modules. And modules or modifiers are something that I kind of wanted to be easily add to the particle system. And so this way, it's not like this particle system can be upgraded very easily, as long as I build a smart enough system where it handles it. I'm okay. I'm kind of somewhat happy with it. I feel like I could do a better job of it. So if anyone who's watching this video and sees the code and is like, oh yeah, there's a better design pattern to make this easier or better, or not design pattern, maybe if it's not a design pattern, then maybe a data structure. Mind you, I never went to college for computer science. I'm self-taught for the last over 20 years. Self-taught, and now I'm a software engineer. I went from like a simple web designer all the way straight up to an engineer. So a lot of work, a lot of studying to self-teach myself all this stuff. But like I said, I might not know the right design pattern or data structure to use because I didn't have a formal education. That's why I never were able to work at Google, because I never went to college. I was told that because of that. Oh, you never went to college? We can't even talk to you in a normal, smart way. I was like, all right, sorry, Google. All right, no big deal. But I digress. I don't even want to work at Google anymore, to be honest. I give up on that. Now I lost train of thought. But yeah, if there's like like I said, the way I'm building it, it's not necessarily the ultimate way of doing it. It's just my way that I came up with how to build a particle system, and it kind of uses a bunch of cool new different things we haven't done in this series yet. Okay, so since I'm done explaining to you what we're doing, so we can probably look at some code. We got some small changes to fungi in our shader file. Very simple. Like we have our create function. I just set it up so we can pass in the transfer and feedback information. Shader builder, the same thing. I added the ability. I put some default values, and to tell if it's interleaved or not. And then on our GL class, I did some simple defaults and other small simple things that are no big deal, but when you're dealing with shaders, I just kind of did some extra defaults and then passed in the ability to change the interleaved. Same thing with create program inside our GL. Because the original source code, I had everything as separate attributes, because we did transfer feedback everything as multiple buffers, and now I changed it to this line of code where by passing in the value, we're going to use interleaved or we're going to use separate. So this way we can use both, and these are just more defaults. But these two are some of the bigger changes. And that really was all I needed to do for changes to fungi in this lesson to deal with it. So this is our test page. So I'm not going to go through every individual line, but I want to go through chunks of code to give you an idea, because it's really just JavaScript and it's just theory. And we've done a lot of this before, except the interleave and stuff. So I just want to show you what our particle effects looks like. So we have our particle system. We say we want 9 particles. We set the mesh. This is what creates our draw buffer, because our mesh is just a single vertex. So we're just going to duplicate this single vertex for 9 times. If we set mesh, we can probably create a quad, so we'd have to pass in several vertices and then normals, UVs, and special. In the next video, if I do particle system, I'll probably expand to quads. But for now, we're just dealing with vertices, just individual particles. So this defines a single particle as a mesh, and that's what we're going to duplicate. And then I had a module, and as you see, there's different modules I have. So one module I have is called position, and it has something called placement. It's like how do we place the particle? And I have something called just test data. But as you can see here, I also have we're going to see later. It has a circular segment. So I can say I want the module, but I want to use this placement function, which then put all the particles in a circle at a radius of 0.5. So if I say 9 particles, let's say, okay, you got 9 particles, but you want it in a circular way, and at a radius of 0.4, it then kind of subdivides the circle into 9 pieces and places each vertex there. So that's what I kind of meant by modifiers or modules. These ends up becoming settings for our particle system. And each module, each modifier is a set of settings. So like that's placing, and radius ends up being a setting for a particle system. But that's based on an individual module that we're going to apply. And I have a velocity and a color module. And at the end, we end up compiling it. And then we just add our particle system as a renderable to our scene, and done deal. And this is what it looks like. Very simple. That's just test data. And that's just our test position. And it generates all our shader code for us. So it knows to create our particle position. And those are particle positions. This is the feedback vertex shader. And all it knows is to V particle pose is our write, and that's our read. And they're actually from the same read and write buffer. Because we were able to read whenever we write, we need to read from it too. So that's the shader code, just like we did before. But all the shader code now is generated by us. Or not by us, is generated by the particle system. That's also one of its responsibilities, is to take all the information from our modifiers, our modules, and compile a couple of shaders. So we have our feedback shader. This is what modifies our read-write buffer. Then we have our draw buffer, our draw vertex shader. And it knows a position is coming from our draw buffer. It has that single vertex. And then here's our particle pose from here. It's from the exact same read and write buffer, and we read into here, and I set it up this way where it knows that there's always going to be a local position, vec3, and then we just modify it. So everything that's kind of not aligned correctly, they're just dynamically kind of input into a template. So we have like templates of shaders. So that's our particle system. So let's look at the actual code for the particle system. So we'll just go straight to the top. So here's our transform feedback. So in the beginning, we're going to have some defaults. So here's our buffers. These are 2 VAOs, a lot of comments, and that's our transform feedback. We keep track of our buffers. This one's for drawing. And since it's interleaved, and I have something called definition that saves the stride and the offset values. That's what definition is. And vertex count. How many vertices are inside our draw buffer? Now I also call static buffer. Originally I called it read and write, but I decided to use the actual names when we use the modes. So this is static buffer. This is our read only data. And this is our dynamic buffer. This is going to be read and write. And like I said, remember, we're going to have two. We're going to alternate back and forth. When we're dealing with writing, we're going to have duplicates. So we're going to have just one copy of our data, just one copy of our read-only, and we're going to have two copies of our writing. And run index is the thing that that I store to alternate back and forth. It's either going to be a value of 0 or 1. It's going to access element 0 or element 1 in these arrays. So that's just kind of the properties of our transfer feedback. And then we have this function, which takes in a bunch of information and interleaves the data and calculates it, and then saves everything in the definition. This is all just JavaScript stuff. I don't really need to explain it. You can kind of look at it and get an idea of it. And there's plenty of comments here to make it sure it's easy for anyone to follow. I had an example of how to manually put the data in. The data looks kind of like this. I give it these are the arrays of information that I'm passing in for feedback data. Then I kind of defined each one, like what's the name of the variable that I kind of want to use, how many components is there, you know, like X, Y, Z, and then I defined where they're being used, like their location in the shader. This should be the location in the transform feedback shader, and this is the location of the drawing shader. So we need two locations, and then this one kind of tells you where it's being used. So if it's right draw, that means this let's say this buffer or this array of information is going to be part of the write buffer, and it's going to be also read from in the draw VAO. So this kind of defines which VAOs these go into. So it goes into the write and draw VAOs. This one only goes into the read VAO, and this one only goes to the draw VAO. So like our color, it's not going to be transform feedback, but it's still going to be a color per instance. So that's why it's only going to go into our draw buffer. But this static thing, this color can actually be saved with velocity. So I can interleave these two together and not be a big deal, because I don't need to read it. I can have the data interleave together, and this one I can just read it in our transfer feedback, and I don't have to read this. I don't have to bring this into our transfer feedback, but I can keep them interleaved. So this way we can, like I said, we only need 3 buffers total to handle the transfer feedback. And that's what the data kind of looks like when you pass it into this function. That's where the FB data and FB information is. It helps define everything. It's the definition. And then end up merging the data together, and some of that information helps compile, you know, the offset and the stride and everything else. So like I have like stride here and something else somewhere. I update the count inside our FBF. The FB info is kind of like something that gets passed around and eventually gets updated, and it uses structs. You can see my C# and C++ coming out as I'm actually creating like functions that all it does is define a struct. So we have interleaved definition, and you know, it saves our stride, our park. Like I should really name these into attributes. To be honest, it should be attribute count and attributes instead of parts. Like it's sometimes I'm just kind of hard finding terminology, but these are really attributes, how many chunks of data exist in a single element, but only during the video that, you know, I should just call them attributes. So it should be attribute, parts, but whatever. You guys can change it as long as you get the idea that parts means really attributes. How many attributes are inside this one element of information? And this is just an array of attributes. And then each attribute is then defined here. What name variable it has, how many components it has, like, you know, X, Y, Z, X, Y, its feedback location, its draw location, the value where it's used, and eventually its offset. So this becomes an array in parts. Say I call them chunks. So this should probably be called element attribute. That should be called attributes, and that should be called attribute count. and interleaved data, a definition is to be fine, or I can just say interleaved element definition. Now that I'm all said and done, I can actually better names for it. But when I was programming it, I just couldn't come up with the better names for it. So those are the structs, and here's a constant enum. Again, this is kind of a very C++, C# thing to do. But I just define the enums, and I use binary. I use Bitwise Operations. So I have like 1, 2, 4, because this is binary. So with all, add them together that makes 7. Draw read is 5. Write draw is 6, because it does write, which is 2, and draw is 4. So binary wise, this is a value of 6. So again, this is something JavaScript programmers aren't used to. But if you're dealing with C, C++, things like that, using Bitwise Operations to combine features as an integer value, very common in use, very useful. Most people that I deal with when it comes to web development don't really realize how useful this can be until I teach them, and they're like, "Oh my god, this is kind of cool." But again, this is stuff like if you're into low-level programming, you're kind of used to. All right, so that's how interleaved data looks like. There's a function. Very simple. We've done this before, like billions of times. Set up our vertex buffer. Yeah, this is for our drawing. So we pass in our draw information. Interweaves it. Right now, I only have vertex data and vert index. At some point, I'm going to add like vert normal, vert UV, things like that, and then interweave them all together. Or actually, you know what? This is right interweave together. Yeah, this vertex data and vert info is the same thing as FP. So this is an array. I should really name these correctly, so I know these are array just by naming them. So yeah, this is an array, like I showed you down here. These are actual arrays that I had originally. So that just my float 32 array. So yeah, so you pass in all our like normal vertex, whatever, and it interweaves it, creates our buffer, and then defines it on the GPU. Transfer feedback. This one creates our transfer feedback buffers. I got to loop through and define which one is which, because I'll have all the data together. And remember down here, I showed you that it had its definition, like what mode it is. You know, read, draw, read, write. I need to split them out because, like I said, I pass it in one big array. But then this part splits them up into dynamic or static. So they get split to where where do they belong. It uses the bitwise operations. So here's like a bitwise operation which I'm checking to see is it in the right mode. If it's not equal to 0, then it means it belongs in dynamic buffer. Else it belongs in the static buffer. So if it's not right, if it doesn't need to be written into, then it's automatically a static buffer. I had other things in here, but it's kind of worthless. If it's not right, it's just read. So like I had like if it's read or if it's draw, then it's a static buffer. So we split the data into dynamic and static. If static exists, we interleave the data and then set up the buffer. If it's dynamic, we interleave the data again, and then we make 2 copies. We create 2 buffers. And you might see something abnormal here. I'm creating the buffer. I'm putting it into this variable. And by the process of chaining, this value then gets dumped into bind buffer. So if you're not, it's the same. Like some people might not used to seeing something like this. So it's the same thing as me just doing it in here and just passing in the value. So it's the same thing as this. So I put that into there, and that gets into there. But since I want to save a line of code, I don't. Because I'll never see this code again. So some people say this makes it very readable. But if I'm ever going to see this line of code ever again, I don't care. Overall, I get it because I do it so often. But some people don't like this because they don't consider this readable. But that's what I'm doing. And then just unbind the buffer. So this one creates our the buffers are read only and our write buffers. Then we have setup feedback. And it's a loop, so we're going to create two VAOs, and we're going to have one VAO. This is going to be like A and B. You know, we bind our read only. It loops through our attributes, and then adds in the information. We have the component, our feedback location, our offset, our stride. All the information there, and so it just it defines it into our buffer. So there's all the VAO definitions right here. Same thing with our write. If it exists, it does it. When it's all done, it creates our transform feedback. I didn't do the shortcut, I guess, because it was too long of a line, because I want the comments to kind of be with visually there. So I wrote it the right way, more readable version of it. Transfer feedback is just like a buffer. We're just defining it as something that's writable. So we just bind our feedback, and we say this buffer is belongs to that. It doesn't belong to that VAO, because we actually close up our VAO. But at this point, for every loop, we're defining our A and B for our transfer feedback. It's not. If you've been doing this long enough along with me, you're so used to just creating buffers and stuff all the time, from time to time. And then our setup, our draw. I have a one to do, because I haven't done like index yet, like to create a quad. So this is incomplete, but overall does what we need for this video. It's the same thing as our draw feedback, except it just defines our drawing VAO. This one binds the stuff for our vertex. Then it binds our static if it exists, and only binds the static if it's set to draw. If a value is not set to be part of drawing, it won't be included. So it only includes what's for drawing. Same thing when it comes to dynamic buffers. If it's not defined to be inside drawing, it does not get added to it. And that's it. So this builds all our stuff. And then when it comes to running, it's almost the exact same code from the previous video. We alternate. We tell it which shader to use. We bind our VAO. We bind our transform. So let's say if the run equals 0. So if let's say we're going to read from run index, and then we're going to write from next index. So it's like A and B. So, and that just defines which feedback we're doing, so we can just very easily pop it in. So this executes our transform feedback. Then we switch to our draw shader, and then we draw by using our next index, or like B, drawing, and then next time will be A. And then we just save next index to run index, so the next time around we know that next is actually the current, which becomes the new A, and then new B. So like I said, this handling it, drawing and executing all our transfer feedback, and it just handles transforming our data into interleaving data. And that's all it does. Overall it's a very small object, and but it handles a big part of our particle system. And our particle system is a renderable, has a lot of information. Right now it's going to have just a simple draw mode. It handles our shaders, keeps track of our shaders, makes a copy of this object, which handles it. Mod stack is when we just add modules or modifiers to our vertice. This is just string that helps save chunks of code that needs to be part of the shader. Every modifier or every module is going to add to these strings, because all it is going to update this. Like here is, let's say, our draw shader, and I have something called attributes, varings, and these are just like little place markers. So I'm going to compile all the code and then take this template and replace these little markers with the actual code, and that's really how I'm generating shaders. for the transform feedback. So it's just a bunch of templates, and like I said, I just replace it with the actual code that gets generated. And the actual code that gets generated is stored here. So that's why there's attribute code, vary code, main code. And that belongs to feedback. That belongs to our draw visual shader. That one belongs to our draw fragment shader. And this kind of keeps track, when I'm building the data, one module at a time, I keep track of the current location of our attribute location for feedback and our draw. So this way I can have a nice continuous 0 to, you know, whatever maximum number of attributes you can have. And we have to keep track of our right variable names, because the way you update the shader, when you create the shader, you have to tell it all the attributes that are like right here, v particle pose. I need to have an array that has this as a single element, that passes that into the shader to say that variable name is a transform feedback value. It's so, like I said in the previous video about particle effects, we went more into detail about how each line of code works. Mesh, like I said, remember this is, like I said, we're going to apply our mesh. We have vert, we have UV, normal, index. It just combines the data into an array of arrays, and then it kind of defines. It's kind of like a quick shortcut. Instead of like where we deal with transfer feedback, it's going to be more dynamic. Since meshes are very common and well defined, we don't need to constantly define these manually. So that's why I made this quick function, because all these are always going to be the same. Our vertex is always going to be 3. Our UV is always going to be 2. Our normal, that's a boo-boo. That should be normal. I have UV, but like I said, I haven't made this with quads yet. So these are probably not. They're just copy and pasting of each other. That's why these probably won't work very well. Norm. Save. So I don't make a mistake later when I do quads. And it calls a function like add draw, but I'll talk about it a little later. Transfer feedback. And then when it's all said and done, it tells it, okay, here's all information, create our draw buffer for the transfer feedback. Our draw function, it overrides our renderable. All it does is it calls our transfer feedback's draw call. All our modules are going to call one of these 3 functions, and all it does is basically, what do we need to update? So if it says, okay, this module only needs to add information, is a read feedback read, so it knows to increment that location. It creates this chunk of code based on some of the values that come in, and it knows what kind of bits of code to put in, where to save it. Same thing with these. This one creates our attributes, creates our out values, and then adds extra code to it if need be. Add draw, same thing. So like I said, I'm just saving all the bits of code and trying to streamline some of so we don't have to, anything that duplicates very easily in templates. And like I said, all that stuff kind of just updates. Those 3 functions really just updates these things. It just chunks of code that our modules create. Let's see. And then we have, what else? Add module is very simple. It just checks to see if the module exists, and then just adds to it, gives it the name, the mod, and mod parameters that you passed in. Same thing, just get module, and then compile, goes through that stack, because I have right here, every add adds to the mod stack. So just a stack of modules, and I don't know why I did that. So now everything's open. And compile, let's say it just goes through that stack and just compiles new compiled data. That's a struct that's reusable. It's down here somewhere. Is it compile data? compile data is just keeps tracks. I should have commented this more. I forget. It's like the name. I kept everything as separate arrays because it's easier to keep them as separate arrays, because then I can easily pass it into our transfer feedback, because they expect things as separate arrays, like make it easier. So it's just like a simple struct. But this thing is kind of saves and compiles all the data for our stacks. So like I say, I call it compile data for the compile function, and I call it FB data, and we pass it to every module. So we say, okay, here's a reference to this particle system. Here's the parameters that were passed in, like the settings for that module, and here's our compile data. So it's an object that gets shared, and this object stores the actual output of every module, and also gives every module the opportunity to go back and see information of previous modules that have been added. So you kind of have to add modules in the right order. For the velocity module, it has to happen after the position module, because I gotta have certain things in velocity that checks to see what position it exists first. So it'll look at the position data, and then apply data that's related to velocity. So that's why I allow this compiled data that gets updated by each module, and each module has reference to the previous module, the final output, if that makes any sense. It's kind of like I said, I'm compiling all the information, and every new module has access to all the previous information that's been completely generated. Once all the modules are done, we can then just take our templates and do our replaces. We can see the output. Since we have our shaders all compiled, we just then create our shaders. We create a single material, because the renderer I built is built off material, so it needs a material first and then a shader applied to a material. So we have to create this fake material so the renderer can run just fine. At some point, I'll figure out how to build a renderer that doesn't need a material. But like I said, materials are required for my little renderer in Fungi. And then when we're done compiling everything, we pass in all the data that was generated from the modules, and all the information from the modules, like all the definitions, and how many particles we want, and then finish building the transfer and feedback. And that's most of the particle system. It's like I probably wouldn't explain it too much, but and there's modules, and the modules are, like I said, they're just kind of like little plugins. So we have modules, a struct, and it's just a simple class with a run function, and it just executes based on what it's defined. And I have something called placement. So each module then has little bits of code to help it along, like what var name I'm going to use, what are some of the main codes that I need to apply to the shader to get it to do what it wants. Like placement, I have like test. This is what defines all the positions as a test data. Then I have a circular segment, which defines the starting position of the vertices, but in a circle way. But you can make a bunch of different placements. That's why I kind of built it this way, so it's kind of quick and easy to check. So like param placement, I checked if it's undefined, but I use it right here. So placement, and then I kind of call it. So it becomes it's kind of like a function pointer, essentially, that I'm doing, making the function pointer a string name. The reason why I'm doing this, because I need this to be serialized. So I need to be able to save this out as like a text file and load it back in. So I'm doing a lot of little funky things like this, because the data in the end needs to be serialized. So that's why even though I'm using like function pointers, but I have like a string that kind of assigns to a function pointer. That's why I have like a placement, but then I added it as a struct, but with a named index. It ends up being like a dictionary. So that's like the key name, like the actual function name. It becomes like an actual text name that I can actually easily connect to. That's why I have it like set up this way. That's why it looks a little funky. But placement is a struct. I can actually just pass it with brackets, like a dictionary, the name of the placement. That becomes kind of a function pointer. And then as a function pointer, I then can call it. Oops, don't want to undo things. So that's the only little tricky thing you might not notice, but this is kind of very, again, another C++, C#y thing for me to do. C++ does it differently because you have actual pointers, like real pointers and stuff. But like I said, it allows me to serialize the data. Like this is JSON data, so I can very easily load this back in. And modules are also text-based too. It follows the same rule. Modules is a dictionary, and position becomes one of the key names in the module structure or module dictionary. So, like I said, it's all for serialization. It's all to save the data and to load it back in very quickly and easily. That's why I'm doing this little funky stuff. And I really don't need to go, like, velocity is the same thing, color is the same thing, but they work in slightly different ways, but they follow the same rules. It has a placement, but you can name it whatever you want because it really depends on how you want the module to work. You know, like color has a placement too? Yeah, I guess so. In case I want to do little funky things with everything, but I kind of create something called test. It doesn't have to be called, like I said, it doesn't have to be called placement. You can name it whatever you want because all this information is the context of this class only. So you can make the module any way you want as long as it has a static run in it and it knows to, call, it knows how to save the data back into the compiled data class. Just how to add it back in the right way, and what functions to call in the particle system to add code that will gets compiled into our shader. And that's our entire particle system. This probably took forever to explain, but yeah. So there you go. That's our particle system, and like any real particle system, it'd be really easy to just say, well. Just say, okay, here's a position, but I'm adding some new settings to it. Like I want its placement. So it's going to call that function circle segment and it's going to add it for that information or that radius. So if I now refresh, now it's a circle. Perfect. That's exactly what I want. And, we see our data right here, our shaders. But let's say I want to add a new module. So I'm going to say, okay, add our, I don't want touch on. So let's say I'm adding the new module color, and I use the test, and there you go. It now adds color, and it alternates back and forth based on how many particles. It is RGB, RGB. It just repeats. And the thing you might not notice is that now our draw function has particle color being added to it, and it knows that it needs to pass it to our fragment shader, so it knows to add out variables, and then it knows to kind of update it. So that's all part of it's all part of the module. The module, like I said, the module is programmed to handle those little bits. So see it has frag color equals that. That belongs in our frag shader. So that's it. Frag color equals that. That's the code. It just plops in there, and like I say, it calls this function add draw, and it adds in our main color draw frag, which is this chunk of code. Like I don't need to do this. I can just hard code this right into here, but this makes it easier. It makes a constant out of it, kind of, not really, but it's a constant when it compiles, but it's a modifiable constant. And I define it as a vec3. So this way, when it creates it, it knows it's a vec3. And like I said, it adds these actual bits of code to our shader, and it generates it. If you want, we can add we can add our velocity, and our velocity has a function for test, which just adds simple test data, which I think it just makes everything go up. But I have the test data changes the velocity per vertice. So the newer the vertice, the faster it traverses, like the faster the velocity is. And let's see. And like I said, it adds code in here. So it has that bit of code in there. Then it knows, so it has a vParticle position, and then it knows to modify it after the fact. So I just add pluses to it. So you could, everything kind of has to be written in a certain way where everything kind of connect together like Lego pieces. So that's the only thing you have to be careful when you're building these modules. So every piece needs to be able to, you have to structure your template and all the code, or all our shader code, in a way that kind of just can just add to it to itself one after another. It kind of, as a, like I said, like the position does this, but then velocity knows that v position exists. So all it does is say, well, add my velocity value to it, and like everything can just compound after that. You know, just one after another. If you want, I can use a different setting for velocity. Normal, I have something called normal position, and what normal position does, it actually, normal position actually goes and looks up data from position and then normalizes it and uses that as a velocity. So let's see. So what that means by normalizing the position and using it as velocity? Well, if you normalize something, especially if it's in a circular way, if it's a circle and you normalize it from origin, it's going to then explode away from origin. So if I refresh, and there's the animation. By changing that velocity function, I went from going test, which shoots it up, to something called Normalize Position, which, like I said, takes the position and normalizes it and uses that as a vector for velocity, as a direction of movement. So very quickly, I'm able to make an explosion type of thing. So if I want, I can just increase the speed a little bit. Let's say 1, and the explosion will probably happen a lot faster. Refresh. Boom. And there it is. A very simple particle system with modules that compounds all the codes together. And there you go. And this is really just the starting point. Like I said, I probably need to go into Unity, look at their particle system list of like properties and options, and really just sit there and just look at all the pieces and then build them little by little into the particle system. Or anyone else can do it too. Like, this is kind of like the starting point. There's always room for improvement. I'm sure there's better ways to go about it, especially defining all the code that gets compiled into the templates that then creates all the shaders. But, you know, so far so good. You know, like I said, we're very easily able to change how certain things work. I can change the radius to be 0.1. So this way the circle is much tighter. There you go. Now it looks more like poof, more of an explosion. See? And this is how particle system works in Unity. You just go in and you change settings and just refresh it, and then you see the effect updated really well. So this is pretty cool. This is pretty neat. The whole point of this was because a user asked me he wanted me to create an effect of a sun. And he showed me some videos of it, and I went to look, and it's Unity tutorials how to do it. But it's super easy to do it in Unity because you have a particle system that has all these features for you. It's super easy. You know, all you have to do is just put the right information in, and you just have to know how to use the system just right to produce that effect. And you got to put the right textures in, whatever. But overall, you don't have to sit there and figure out the math. You don't have to write the shader code. You don't have to figure out how to deal with the data and the buffers. There's so much that goes into a particle system that you have you don't realize it when you look at a Unity tutorial. You look at Unity tutorial, you're like, oh, it's not that big a deal. This video shows you it's much more bigger deal than that. It's not just simply toggling things. When you're dealing with something like WebGL that has nothing there, you have to bring everything into WebGL. You know, you have to kind of be smart about it a little bit. You really have to build everything. I think that's really the whole point of this video. So at some point, I'm going to do his sun, but instead of me hard coding it like every other effect that I've done, let's do this the right way. Let's build a real particle system like Unity that allows us to, as we slowly try new effects and we add in new modules and new functions and new things to it, we can then eventually at the end of the year or the end of 2 years or whatever, we have a full-fledged particle system on par, if not better, or almost as good as Unity. That all you have to do is just toggle a bunch of settings and then press play, and there's our particle effect. So I'm sorry if I'm not building the sun that you actually wanted to, but this is the precursor for it. Like I said, instead of me just hard coding it and just teaching you how to write the shader for it, how about we just build a particle system that does it? So this way, we're still learning the shader, we're still learning the math, but we're understanding how the particle system really works in systems like Unity or Unreal Engine, things that make it so super easy. You think it's so easy. It's not. There's like everything I told you about, like how to handle the data. We have to be efficient about it. We have to interweave. I guarantee you know to interleave the data. With all that information, you have to optimize it as much as possible. I'm sure they're using some kind of transform feedback because the GPU can do the math much faster than the CPU can. You know, because it's it's parallelized, has multiple cores. You know, things like that. So, yeah, I had fun. This took me a long time to put together. I had a lot of failures. Like I said, like I didn't know how interleaved data would work in WebGL. But like I said, originally I thought I only needed 2 buffers. I ended up realizing I need 3 buffers. But yeah, like I said, we very easily got an explosion. And you know what? Let's try this. 20 particles in a circular fashion. Everything is going to explode from the center. Refresh. Poof. There we go. Now it'd be really cool if I was able to change the velocity just a smidgen. You know what? Why? I'm gonna hard code something, but just for fun. 1.2. No, 1.001. I'm gonna change the V velocity, the Y position, just by a smidgen, because I want it to explode but then go down. Like add a little bit of gravity. Refresh. Yep. Are they? That doesn't look like it. Normalize position. X, Y, Z. Maybe it's not big enough. Oh, you know what? Yeah, let's try it. 1.1. Refresh. I was so sure that would work. Oh, it is going up. It's going slowly up. I need a bigger number than that. Refresh. I don't know. Fine. I'm gonna do this. If it doesn't work out, I give up. Oh, that's weird. I thought it would change the Y position. Times 3. I thought it would change it to make it go a different direction. Damn, I suck. Oh well. That's what I get for trying something. Yeah, normalize it. I would. Because I already added speed to it. That's probably why. I probably already added speed, but I'm multiplying by it. It should change it. You know what? Screw it. One more time. Times 100. It's got to have some kind of effect to it. Nope. No, it's still going straight. Oh, well, I give up. I don't know. Oh, you know what? Let me try the empty cache. Does that work? Nope. All right, I give up. I don't know why the Y position of the velocity isn't making the particles. Are they going up now? No, it's just an illusion. They're going straight. So, yeah, whatever. I give up. I'll figure that out another day. I'm going to make another module. All right, let me just end it here. This is probably a really long, boring video about stuff. It's a nice Sunday. I got to do things with the fams and stuff. All right. Hope you guys enjoyed it. Hope you got to learn, get an idea of what really goes into a particle system. Like when you guys look at a Unity tutorial, it looks like it's super easy, but you got to remember in the back end, it's a lot more complicated than just toggling a bunch of settings. You know, you have like modules or modifiers. You got data you have to deal with. You got to deal with buffers. You got different types of shaders that are running. You got to generate shaders that does the mathematics for you to kind of speed things up. Like I said, there goes a lot to actually creating a particle effect. It's just the game engines make it look super easy. But this whole series is basically the idea of building a game engine. So you're kind of learning that it's not, even though it looks easy at the end, getting to that point is very difficult. It's a very long process of discovery and experimentation, and you learn a lot. You learn a lot of how to deal with data. Like you learn like interleaving data doesn't take, when you're writing interleaving data in a transfer feedback, it doesn't take stride into account. Like I didn't know that. Now I learned that you have to handle data in a different way, because else you're overwriting memory. It doesn't create a memory leak, but it causes memory issues, and that, you got to be mindful of that. You don't want to mess up memory, because then it screws up your effect, and it's hard to debug. Especially WebGL makes it super hard to debug. It took me all of Saturday to realize that I was overwriting data. I didn't realize that, because I thought I was taking stride into account when I was writing. It was just overwriting data. I forget how I tested it, but I just kept messing around, and I started realizing, oh, data's being overwritten. Oh my God, this was going on. Okay, so yeah, so hopefully you learned a lot in this video. Like I said, now you guys know what it takes to build a particle system. Like this is the bare bones. Like I said, it's not the perfect way of doing it. I'm sure there's a better way of doing it, but it's a step in the direction of how to go about doing it. One method of way you can build a particle system from scratch, and things you have to take into consideration, like data and serialization. Like I said, I had to build it in a certain way so I can serialize it in the end as JSON code, so that I can then incorporate it back into the system. So you can reuse it, you can edit it, things like that. So like it makes it easier for a UI tool to kind of just modify the data and just bloop, plap it right back into the particle system, and then run it again. So like, yeah, like I said, you have to think of things like that. So yeah, I'm tired, and this is probably the longest I've ever talked, and probably a lot less ums, I think. Hopefully, I'm really bad at public speaking. So the usual stuff, like and subscribe. Thank you, Patreon members. I got to find a way to kind of display on the screen all your patrons. Like someone came and gave me $10. Oh my God, thank you. I really, really appreciate it. I need to contact you to see if there's anything particular you want me to work on, as a thank you for the $10 donation. But again, thanks for anyone who just comes and subscribes, because like I said, I've lost my partner program, and I can't get it back until I get like at least 1,000 subscribers and at like I think 4,000 hours of views, which I'm only at 2,000 hours. I think so. It's no big deal. This whole year I haven't made a single penny. Like you won't get your first check until you make $100, and I'm at like $20 or $30 after a year. So I haven't made any money on YouTube. The only money I've actually make is through Patreon. That's the only money making thing here. But again, like I said, I always say I'm not doing this for money. I'm doing this because I want to do this. I love graphics program. I want to learn it, and there's not enough material out there to teach you these things. Like there really is no tutorials on how to build a particle system. I think this is a great video. I think there's one or two I found, but like from DirectX, from Microsoft. That's about it. But I don't think you want to go through an article about DirectX on how to build a simple particle system. I didn't bother. I was like, I'm not reading this crap. I'm not a big fan of Microsoft and their documentation. But I digress. All right. Now I'm babbling on and making the video way too long. See you guys at the next video. I might be going back to voxels, or I might be trying a simple effect that I saw recently on Twitter. I'll let you know. See you guys in the next video.